That's fine. You can have fun with convolutional neural network. Yes, last class you learned how to use deep neural network in a dense points of view when everything connected to everything. We also call that kind of neural network feed forward because it feed input and just pass it to the next layer every time, and that's called feed forward. But what was the problem with feed forward? Do you remember what was the problem with that? Anything remember? Anybody ideas about feed forward last class? It was great, no? You could design layers, especially using TensorFlow, and what was the API Kera? You could easily define so many layers and just give input data and learn all variables, but those variables were a lot of variables because the structure was dense, so you have lots of variables to learn from data. And especially for some specific inputs that they have some spatial relationship in those data, like there is lines, pictures, lots of data that are related to each other, like corners, for example, and then becomes, for example, objects. They are related to each other. You can make them as a line, but in dense neural network that we had last class, we consider them as all flat or as a matrix. We just consider that as a matrix. We don't consider that as an image that are related. But that makes the neural network so actually big and computationally very, very expensive. Computationally expensive means need lots of memory and CPU or GPU. But today we want to see how we can make that better. How we can, instead of considering a picture as one array, like a flattened array, we consider exactly as a picture and find those relationships between pictures using convolution. Convolution gives us this amazing benefits to look at the pictures that are related to each other and find that relationship using mathematical points of view. Yes, that's kind of neural network called convolutional neural network. That's what we want to talk today. Let's see what that means and how we can use this. Convolutional neural network is good for data that are actually, they have some a spatial relationship between those data. It's not just an array. It's not just a table or database. It's actually image that are related to each other. Pixels are related to each other. That relationship called a spatial relationship. If there is a spatial relationship with the data, convolutional neural network is the best way to detect objects or actually learn from those pictures. Okay? So problem in dense neural network was that each neuron was connected to every other neurons. So if the input is image, so every pixel need to get connected to one neuron, and you're gonna have lots of neurons in this case, and it's not possible. For example, if the image is, I don't know, 100 by 100, you're gonna have 10,000 neurons. It's not possible, and process gonna be so expensive. So the idea is, instead of connecting every pixel, we connect a patch of pixels. So this is the image that show everything, you know. Instead of talking 100 words, we can just show a picture. So in this picture, you can see the relationship between this patch. This patch, if there is some pixels here, they have relationship. We can summarize this picture with this patch with one pixel. So, and that patch called receptive field. So we just need a kernel. We just need a kernel that is another matrix. Most of the time 3 by 3. Over here is 4 by 4, but doesn't matter. But normally kernel is odd numbers, like 7 by 7, 3 by 3, 9 by 9. So anyway, this is called kernel. So normally kernel find this spatial relationship, this spatial structure. If there is any relationship in this picture, for example, there is a line here. If there is a line like that, and we choose the kernel like this kernel cannot detect those pixels that are belong to that line. If I'm talking about detecting, means it gives them more weight. It's gonna take those features out. Anyway, we have receptive field. Receptive field is this. Receptive field. So instead of working for all pixels, instead of having for all pixels one neuron, we just need to have one neuron to act in that receptive field. So the operation is going to be much less. What else we can do? So the neurons only see those few pixels. And it detects local patterns based off the kernel. And what else? And this, let's clean this up. These local features are shared across the image. Another point is we can slide this patch or this receptive field around the picture and find everywhere in this picture that pattern. So that's amazing. So when we do this operation, the result gonna be another picture. If this picture, for example, is n by n, and this picture is, for example, m by m, and this kernel is k by k, what is the relationship between m and n? Anybody can guess? Is it m smaller? Is it m smaller than n? Or bigger than or equal?
Should be smaller than n.
Should be smaller? Should be bigger? Should be equal? It can't be bigger. It depends. So it depends the size of k for sure. So because when we are for example, is 3. When we are sliding this window, for example, here, a sliding window around, across all the pixels. But because of the borders, we lose one pixel. So generally, the size of this, so the M will be n minus k plus 1. Right? So for example, if it's 3, this gonna be, no, okay, for example, this is 100, and this is 3. N is 100, and k is 3. So M gonna be 100 minus 3 plus 1, 98. It makes sense because we are sliding that 3 by 3 around. When you start from the first part, you're just gonna lose because you are making in this pixel, so you are losing this and this. So you actually lose 1 here, 1 here, 1 here, 1 here. So it's gonna be 98 in each side. So M gonna be 98 by 98. Did you get the point? So you even decrease the size. You decrease the size, but at the same time, you keep the relationship between pixels. You keep those relationships with this operation that we are doing here, because this operation actually get the pattern out, take the pattern out. Because we already learned about convolution before, and we realized how convolution can take patterns out. Like, for example, when I'm talking about patterns, the pattern can be line in that picture, in that a receptive field. It can be corners, for example. It can be different lines, edges, we learned that before in when we were talking about convolution in image processing. Same things happening here. Okay. Any question about this size? Are you agree that this is good way to work in pictures using convolution? It's good way because in pictures you want to find those relationships, and those relationships can take out using this method, using convolution and having a receptive field and having actually kernels, that these kernels are important. And the value of the kernels are those W's that we need to learn. So that the values here, these weights, we can call them K or W, sometimes K, something like that, doesn't matter. Wij, they are the weights that we're gonna learn. Instead of having the weight for each connection, like in dense neural network, we're gonna learn these weights in kernel. And that's gonna be very, very beneficial. And the score gonna change as well. The score, instead of having, do you remember a score was in dense neural network, for just one layer I'm talking about. A score in dense was W X, if we consider X as a features. But here, in this case, a score, this was in dense. And in convolutional neural network, it's gonna be, we can't, it's not like multiplication. Here we have a matrix, we have addition, I or J. What we're going to have here, we have kernel, so let's call kernel K, for example, Kij multiplied by X. So this is going to give us 1 pixel. So let's make this FEQ, for example. XP plus I and Q plus J. If we have a bias, we also need to add it with bias. So look at how changed. In this pattern, it's kind of same. However, I put here K to specify this K is those kernels. I can make it W, it doesn't matter. Let's make it W to be similar. Yeah, let's make this W. But it's not dot product anymore. And this is actually 2. I wrote I and J here. It means this is actually 2 sigma, 2 addition. 1 I, 1 for J. It doesn't matter. You can get the idea. So this is showing the convolution, because convolution is element-wise multiplication. Element-wise multiplication. Convolving 2 matrices together, you just element-wise multiply them together and add them together. So that's element-wise. As you can see, this is element-wise because Ij and here is Ij2. This P and Q is just to specify the receptive field. Okay. If you didn't get all the idea, don't worry. I'm going to explain that more. This was just a general way how this works. Okay. Using a spatial structure. So again, I explained that how this spatial structure help. First, local connectivity. So instead of having a full connection, we just have a local connectivity. So in dense, for all the image, connect to 1 neuron. In CNN, if this is all the image and this is the neuron, you just consider this patch. This is local connectivity. So this local connectivity give actually the benefits of detecting pattern in that field. If there is any pattern in that field, this kernel gonna learn it. This kernel, because we are learning that kernel. We don't give those weights by ourselves. Those weights gonna get learned from data. Okay, so we just make the structure ready. The rest is just same way. Forward passing and backward, back propagation and learning those W's. But we make the structure a different way. Instead of connecting all pixels in 1 neuron, we just connect a patch or a field to neuron. So the connections, the W's are so less. Here if we have, for example, 100 W1 to W100, here we just have, for example, if we use this, we just have 9 W0 to W8, for example. 0 to 99, for example. So we have less weights. That's amazing. And even not just less, more powerful, because we also can detect relationship between pixels or patterns. Okay, and another point is we can share these weights with sliding that receptive field across the image, we are sharing that. Okay, so this means we don't need to have lots of neurons here. We don't need, if for example, we have 4, this is image, raw image, and we want 4 kernel. We want 4 layers for convolution. So we define 4 kernels. So each of these gonna act in this image, and this kernel gonna make one picture, each of them one picture for us. So this picture is n by n. This picture is n minus k plus 1, n minus class. So 4, because we made 4 kernel. For example, 1 for edges, 1 for corners, 1 for, I don't know, any other pattern that we want to find. However, to add nonlinearity, we just put a function of, for example, ReLU here as well, or sigmoid, or any other nonlinearity as well. That's it. So this, in general, gonna be one layer of neural network. Instead of having lots of connections, we just have this connection. This connection is very efficient, mathematically and memory and everything. Any question in this? Let's go forward. You're gonna figure it out more. So here, as you can see, showing how we are sliding the kernel around the image. So this kernel is 4 by 4, but normally kernel is not 4 by 4. Anyway, this, as you can see, that 4 by 4 making that pixel. And we moved it to make the next one. However, because this is, I don't know why this picture is 4 by 4, because in 4 by 4 you can find the middle one. If you want to find middle one, it's very hard. That's why in this case, the result of this is 14 becomes 6, because we are not doing convolution properly. I should change this picture later. So this was the picture that I used for the other university, and I don't know why I didn't pay attention to this part. Why is the kernel 4 by 4? But this is showing something. It can be 4 by 4, but you need to move differently. You need to, as you can see, the next one, it moves, instead of having 1 pixel, sliding 1 pixel is sliding 2 pixel. In this case, you can, that's why this becomes, is 14, and this has become half, like 6. And that's nice, actually. I didn't pay attention to this part. So the structure and the pattern that I mentioned in the last slide, and I said, okay, image is n by n, and the kernel is k by k. The output is, for example, m is n minus k plus 1. Is just in the case that you are moving, you are sliding 1 pixel by 1 pixel. But if you slide 2 pixels, that's gonna be different. A sliding 2 pixels here. In this case, it's actually nicer. It gave something to my mind instead of, because we have another operation later that is max pooling. Max pooling doing something like that. Max pooling actually shrink the file. Yeah, I'm thinking maybe we can do max pooling at the same time too, but don't worry about that. Just that's not important. This picture is is not good picture. I should change that later. Okay, let's clean this up. But this formula is the formula for sliding 1. And we are sliding 1 in convolution, not 2. This picture is not a good picture for that. Okay, so let's see what is the idea. The key idea is CNN exploit the spatial structure of the image. The spatial structure means if there is any relationship between images, it can be captured and taken out. If there is a line there, if there is a corner there, if there is any other features, you can take that out. Take that out means it gives them more weight. Okay, and that's called feature extraction. So feature extraction is actually using filter or kernels to slide over the image and take all the pictures out, or all the image, all the specific patterns out. So this filter can learn all these specific patterns, and the output called feature map. The output is feature map, and when you have multiple filters, the multiple filters actually can get all of those features. And when you are going to the higher level, when you are moving to higher level, these features can detect more abstract features. For example, the first one is edges and shapes and corners. The next one is parts, and the last one is objects. Okay. So the convolution turn raw pixel data into meaningful features. So how convolution works? Convolution is like that. As I said, is a wise element-wise multiplication, and then add them together. For example, 2 by 2 here. I don't know this example is why is this, because we wanted to make it simple. It should be 3. We don't have 2. Anyway, imagine there is 2. It's 2, and this is 4. So these 2 with these 2 multiply together, as you can see, and add together. That's going to be the new value. And this is how convolution works. We knew that from before. And so 3 important things happening in convolution. First of all, we do we select fields, receptive fields. So that's called local connectivity. The first thing is local connectivity. Local connectivity. The second one is sharing filter. And the last one is actually filter spatial structure. All of these 3 happening because of convolution. Local connectivity, if there is connection, and we don't need to do for all the image, just local. Sharing filter, we just need to share the filter for all the image. And filter spatial structure. A spatial structure going to take out this, if there is any relationship between pixels, that's going to get out. And this is going to bring something that we call it, let's write another color, translation invariant. Translation invariant. What that means, it means if there is a pattern, this pattern gonna get detected anywhere in the picture. And even if this pattern is a little noisy, it still can get detected. So this translation invariant means like that. And this is happening because of the convolution. For example, you are detecting, for example, X, and this X is like this. It still can get detected. We can see example in the next slide. So that's called translation invariance. And because of convolution, convolution is amazing operation that give us this characteristic. Mathematically, the convolution acting like that. This is the kernel, and this is the pixel. It's just multiplying them and add them all together to find a new X and Y. So this is X and Y, the position of X and Y. Example, like in this, as you can see, we are trying to detect this X, for example. Even if this X is like that, it still can get detected. Like a little shift, if it's not distorted a little bit, it still can get detected. For example, I use this filter, but we're gonna learn this filter. This is just example how convolution works. But based off the training data, we're gonna learn that actually kernel. So this is the output. If you use this one, even though this we are supposed to find X, for example, but this X is not very nice. X is like a little distorted or get noise or shifted. And still this can get pattern around. Look at this, that's the output. It still can get out some pattern out. So it means convolution kind of keeping the structural relationship between pictures. A structural relationship between pixels actually transferred. So that's why it's called translation invariant. That's why it's translation invariant, what I mentioned here. Okay, here again, this famous picture, you can see the different actually kernels get different features out, like for example sharpener or edge detection or a stronger edge detection. It's just changing this kernel with different feature maps. So the output of neural network after convolution called feature map. So this is one feature map that, for example, you use three kernels. So it's gonna get 3 pictures out based off each of these kernels. Okay, let's see how it works. Implementing convolutional neural network in Python is so easy. You just need to use actually TensorFlow, and Keras is the API that you can use. TensorFlow is a library. Google actually made that. And Keras is just interface to use TensorFlow. We have different kind of interface as well, but this is very good one. It's a very high level. So easily you can do. We use this before in normal dense convolutional dense neural network as well. Here is also the same. Just the layers are convolution layers. How to make that? Convolution 2D, and you specify the kernel and that. Okay, I'm not gonna go more. Next class we're gonna talk. So before finishing, let's explain this picture. This is the structure of whatever happening in convolutional neural network. This is the raw image. Here we have three actually kernel, K1, K2, and K3. And based off each one, we make a new picture, and then we do max pooling. Max pooling is just shrink them. Max pooling is very interesting. So, for example, here is 1, 2, 3, 4, 5, 2, 0, 2, 1. It's gonna find the max. Just find 4. For example, 4 is the max one. Yeah. So it makes shrink it, and then linear that in a matrix, and that's gonna, the last layer is just fully connected layer. We're gonna give it to another layer. Okay, we're gonna talk about that next class. Don't worry about it. Okay, have a good day. I'll see you Wednesday.